Sergio Cocchia. I was born and raised in Italy, and I have a bachelor degree in geology from University of Siena in Italy, and a master's degree in Colorado State University. I joined CH2 & Hill, my company, in 2001, and I've been working with CH since 2001. A bit in Italy, here, Italy. I've been moving back and forth, which was nice. You know, I worked on several interesting projects here and in Europe, and I love my job and I love the company. So today I will present you the results. Some are preliminary, some are final, of a project that I've been working on for the Navy. Joint Base Pearl Harbor-Hickam. Basically, it's a case study of can you hear me, guys? Okay. It's a case study of a sustainable and dynamic, cost-effective approach for the remediation of a petroleum-impacted site. I'm not sure how familiar you are with soil and groundwater remediation terms. I'll try and talk as simple as possible, but if you have any question, let me know. And I apologize in advance if I use acronyms. In the industry, it's crazy. When I joined CH2 & Hill, I had like a Word file that was, I think, 15 pages long, and I would never get used to acronyms. But now it's like, I can't do without it. But stop me if you have any question of any sort, or if you prefer, I can address questions at the end if you have any. Maybe I need to stay here. Oh, that's okay. Okay. So this is a project where we had several phases, and I'll try and cover a bit of every single phase. So first I will go through a brief background and objectives of the project, and then I will cover the different steps that we followed through the process. And it's still ongoing. We're now in the last phase of the project, and by the way, I will present the ex situ chemical oxidation of source area soil remediation at Battelle in 2 weeks. So that is probably the part where I will focus the most. Background. So this is a 1.3 acre undeveloped area in the middle portion of Joint Base Pearl Harbor-Hickam on the Hickam airfield site. And there are future plans to build a joint fire crash rescue station. The lithology for the site is mainly coralline sand and gravel, and the groundwater is at about 4 feet, and is of course tidally influenced because we're fairly close to the ocean, but not too close. And in 1997 there was a release of jet fuel, JP8, from a valve along a pipeline that traversed the site, what is called Stripper P43, which is also the name of the site. The pipeline has since been abandoned, and we started remediation. The investigation and interim response action started in 2001, and then there was a long sort of interim long-term response actions, and the main investigation was in 2009 and 2010. And as a result of the investigation, another consultant found that the soil and soil gas were contaminated by petroleum hydrocarbons. And concentrations were above the soil and construction worker action level, what we call RACGs, which is Remedial Action Cleanup Goals. And we also had product, phase LNAPL, light non-aqueous phase liquid, basically fuel, on site. We had up to 1 foot of fuel inside some of the monitoring wells. Concentrations, as you can see from this table, were pretty high. Diesel range organics, which is the non-volatile part of the petroleum hydrocarbons, were up to 20,000 milligrams per kilograms against an action level of 5,000 for industrial land use. GRO were 5,000 against an action level of 3,400. Naphthalene was 65 against the RACG of 40. And in soil gas, we had very high concentrations of GRO, 40 million micrograms per cubic meter, and the RAG is 4 million. And methane was also very high, 80 or plus, percent against the RAG of 0.5.
So you had a foot of free product even after?
No, before. This is after the investigation.
Okay.
This is the picture after investigation. And so after the investigation, they set up this project, and the remedial action objectives were to prevent human exposure and of course prohibit residential use. We know how to have kids playing in the gravel where it's not an immediate risk because there is no contamination at the surface, but 3-4 feet down there were pretty high concentrations of TPH, of total petroleum hydrocarbon. And the specific objective especially for the source area, was to treat the soil in an attempt to reduce the concentrations below our RAGs, our action levels. This is a snapshot of the site, and so the pink line is our residential boundary, meaning that all the concentrations of soil inside this boundary were above the residential limits. And the blue one is the industrial land use control boundary, meaning that concentrations inside the blue line were above the industrial RAGs. The red one is the source area, which was identified during investigation as where the LNAPL, the fuel, was observed inside the monitoring wells. And that's where we focused the main portion of the project. And as I mentioned, this is right now is an undeveloped area, but part of it on the east side is a parking structure, is a parking area that serves a base passenger air terminal, which is here. There is another facility up here, another facility here, meaning that it's a very busy area. So we had several challenges, logistical problems, and I'll go over it very briefly after. So the project scope again was to conduct several things. The first one we did was ISCO, in situ chemical oxidation bench test, to evaluate several oxidant and activators. Then we conducted a pilot test on site to evaluate, estimate the hydraulic parameters for the ISCO, for the injection part of the project. After that, and this was not planned originally, we conducted ex situ chemical oxidation. I'll tell you more later. After the bench testing, we decided that ESCO was probably a good alternative to ISCO for the source area. And the source area was 0.4 acres. After ESCO, we checked the concentrations in soil and soil gas, and we conducted ISCO in situ this time, injecting in the ground the chemicals, and long-term monitoring and land use control implementation, meaning that no residential use, the site is controlled administratively because they cannot use it for anything residential or even industrial use until the concentrations are below the action levels. So the first part of the project was ISCO, in situ chemical oxidation bench scale test. And we had three main parts of, the test consisted of three main parts. The first one was there was actually a preliminary phase where we went on site, we collected several undisturbed cores, we froze them, sent them to the lab at Washington State University, Professor Rick Watts, who has done extensive research on ISCO, in situ chemical oxidation. And on those cores, we first conducted some analysis to determine concentrations in soil and soil gas. And after that, we tested several, we set up reactors, like 40 mil vial reactors, and we tested several oxidant and activators to see which one was the most effective for our site soil. the last part of the test was to, once we selected the preferred oxidant, we conducted some column testing to evaluate each. We selected 2 or 3 formulations, and we wanted to see how they perform with different dosages, so we could select the ideal optimum dosage for our site soil. Like I said, we collected several cores at 2 locations on site. Here was, this location was representative of high concentrations, DRO, diesel range organics, up to 20,000 milligrams per kilograms, and GRO in the 5,000 range, and moderate, meaning average about 10,000 for DRO and 4,000, 3,000 for GRO. We froze the samples, like I said, sent them to the lab, and they were processed at Washington State University. The initial characterization included the determination of concentrations of our contaminants of concern, which were mainly DRO and GRO, but we also ran some fractionation. From the previous investigation, they found that the main fractions of concern were aliphatics in the C9, C12 carbon range 9 to 12, and aromatics C10, C12. So we analyzed those as well, but our action levels were for GRO and DRO, and that's what we were mainly interested in. Anyway, the concentrations from this, sorry, press the wrong button. So the concentrations that we found were in line with what was seen before doing the investigations in 2010. We had DRO up to 20, 25,000, and GRO, the volatile fractions, up to 5,000 milligrams per kilograms. As part of the initial characterization, we also ran TOD, total oxidant demand, because we wanted to understand, these oxidants are non-selective, so they attack the contaminant and the organic matter, whatever is in the soil, in the same way. So we didn't want to underdose. We tried to evaluate what was the total oxygen demand, and that was a good starting point. And we saw that it was in the range of between 2 and 5 grams of persulfate. We used persulfate for TOD per kilograms of soil. And that was a good reality check, because usually this technology, the ISCO or ESCO, is a cost-effective technology for large source areas if the TOD, the total oxygen demand, is below 10 grams per kilogram. So we were below that range, and we felt good that we were on a good track. So we selected 7 and 9 grams per kilograms for the initial testing, because we wanted to add, on top of the total oxygen demand, we wanted to add some oxidants so we could destroy the contamination. And we had basically, like I said before, 2 tests. The initial RRE, relative reagent effectiveness test, where we tested several oxidants, like Permeox, which is basically calcium peroxide, generic calcium peroxide, Regenox, which is a percarbonate, and then several persulfate formulations. And so we set up, Washington State University did, not me, but the team set up vial reactors. In each vial we had 30 grams of soil, and so we injected the dosage of 7 and 9 grams per kilograms of these reagents, of these oxidants. And the results of these RRE tests were that the most effective oxidant during the testing resulted to be, again, wrong button, sorry. Alkaline activated persulfate, which means we use the sodium hydroxide to raise the pH, a base to create an alkaline environment, and that activates the persulfate, and I'll tell you more in a second. And also the iron activated persulfate performed pretty well. We had significant mass destruction for the contaminants. And the surfactant enhanced alkaline activated persulfate did not perform as well, but we carried on to the next phase because theoretically the surfactant should help to desorb the contaminant, and then the persulfate destroys it. So we wanted to test more to see if we could get good results. So a little bit, very briefly, about sodium persulfate. I'm not a chemist, but I know a little bit. Sodium persulfate is a strong oxidant. As a reference, I usually consider chlorine, which has a oxidation potential of 1 volt. And compared to that, sodium persulfate has an oxidation potential of 2. However, it has a very slow decomposition rate. It's very slow to decompose and oxidize the contaminant. Usually what is used in the industry to accelerate that process are initiators or activators. And when it breaks down, when it decomposes, it generates very strong radicals like sulfate and hydroxyl radicals that have an oxidation potential of 2.5 and 2.8 volts. So that means they're a very strong oxidant, but like I said before, they're non-selective, so they attack anything they find. So we carry these 3 oxidative processes, formulations, to the next step, and we set up column reactors. Basically, we took undisturbed soil, we left it in the cores, and we injected, we simulate in situ injections in the lab. At the same time, we run other tests with homogenized soil because we were a little bit concerned about heterogeneities of the soil. And we didn't see a significant difference between the 2 parallel reactors. The results were pretty similar. For the injection, they used 100 mils wide mouth jars, and I think it was 100 mils syringes attached to 3 millimeter steel probes, inserted inside these columns, and they were injecting the chemicals. And we tried to inject 1 pore volume. Basically, we wanted to saturate all the pores inside this core, inside this little reactor, to try and have contact with all the soil and all the contamination. We let the reactors, the formulations react for 14 days, and during these 14 days we were measuring residual persulfate. So if we had very low residual persulfate, it meant that the reaction was pretty much complete. And for some of the, we saw that the iron EDTA activated persulfate was a slower reaction compared to the other 2. And overall, oh, by the way, these are the dosages that we use. 9 grams per kilograms of persulfate with 800 milligrams per liter of iron EDTA for the first formulation. The second one, same dosage of persulfate with sodium hydroxide, 3:1 molar ratio to increase pH. And the third one, the same as the second, but we use this surfactant, Verusol, 5 grams per liter, which again is supposed to desorb the contamination so it's more available to the oxidants. Like I said, the slowest oxygen consumption was the iron EDTA, and the fastest was the enhanced alkaline activated persulfate column. Results of this column testing was, they were pretty encouraging. We had destruction of TPH, of total petroleum hydrocarbons, for iron EDTA and alkaline activated persulfate between 70 and 80%. The Verusol was a little lower. So we ended up selecting alkaline activated persulfate for the ex situ chemical oxidation, and iron EDTA for the in situ chemical oxidation. So the second part of the project was the ESCO, ex situ chemical oxidation. As I said before, this was not planned. During the proposal phase, actually during the planning phase, there was a decision document after the investigations signed by DOH in the state, saying that the most effective remedy would have been ISCO of the entire area. So injection, like a crazy number, like 1,200 injection points with calcium peroxide. But there was not really much study done with actual site soil to support that decision. And so during the proposal phase, the client asked us to do something different for the source area. And they said we should excavate and dispose of the soil. So we have better chances to achieve the RUCs and clean up the site. However, one of the challenges, as you probably all know, we live in a small island, limited landfill space. The landfill space is rapidly decreasing. The land is very valuable, and disposal costs are very high. So we wanted to come up with something more sustainable and at the same time cost effective. And based on the bench test results, we thought that ex situ chemical oxidation, instead of injecting, we could excavate, treat, mix with the oxidant, and then analyze the soil. And if it was below the reaction levels, we could put it back in the hole, basically. If it was above, we needed to do something else or dispose of it. But it was a risk, because the risk of treating, spending a lot of money on oxidants, and then not meeting the action level was a real concern, and that would have increased the cost of the project even more. So it was a little bit of a risk and challenge. Other challenges, like I said, we were working in a very busy area with other projects going at the same time, so traffic control, communication with all the stakeholders, it was significant. And the last one was that the site is traversed by many utilities, drinking water, stormwater, communication, electrical. It was very complicated to excavate the soil. Like I said, it was a very dynamic approach. On the planning phase, we changed from ISCO to excavation disposal to ESCO plus ISCO plus monitor natural attenuation here, and then there's control. And then very dynamic was also how we implemented, especially the ex situ chemical oxidation, the excavation and treatment part, because we were constantly monitoring pH, and I'll tell you more later, but we adopted a observational approach, if you want, to monitor some parameters and adjust our dosages accordingly. Like I said, it was a sustainable approach. Our goal was to dispose of no soil at the landfill and use local resources and small businesses as much as possible. So not only, and that's what happened, not only we implemented a sustainable approach, we didn't dispose of any soil at the landfill, but we also supported big time local economy. Everything was procured for the ESCO part was procured locally. And the objective for this specific portion of the project was to reduce the source soil concentrations below the industrial RUCs. Let's see real quick. Again, the selected oxidant was the sodium persulfate. Is a process patented by FMC, which is now Peroxichem. Is a big provider of chemicals, and they hold a patent for at least they used to. Now I don't know. I think it's expiring, but I don't remember exactly when. For sodium persulfate, for activated sodium persulfate. And the ratio that we used on site, the dosage was for 100 cubic yard of soil, we used 1,400 pounds of sodium persulfate to achieve a dosage of approximately 9 grams per kilograms. We raised the pH to about 11 using 800 pounds of lime per 100 cubic yards of soil, and we mixed everything with water until we reached a cement-like consistency. It was a sort of observational approach again, because there was not a lot of study on how much water you need to use, so we were monitoring pH, and we wanted to make sure that there was a good contact between the oxygen and the soil, and that's why we use water, which also helps to activate the persulfate. This is a snapshot of the site. We were lucky enough that, when we were working, Google Earth took new pictures on top of Joint Base Pearl Harbor-Hickam. We have a license to use the image because it's copyrighted. This is the site fence, and this is the source area in red. And we set up inside the source area, we set up a sort of a dynamic mixing pit that we were moving as we were excavating. And that's where we were mixing the excavated soil. After mixing, we would stockpile the soil on site. So the excavation, it was, we excavated 1,350 cubic yards of clean soil at the surface to access the contaminated soil, which was about 3,150 cubic yards of soil. The objective was not to remove all the soil. This was only the source area. So where we saw heavily impacted soil based on stain, odor, or things like that, we were excavating a little bit more, but we had budget and schedule constraints, so we couldn't just excavate the whole piece. And like I said, no soil was removed under utilities because that was a big concern. If it actually happened, unfortunately, that we broke a water line, we were not even on site, but those are big problems. And it cost the project quite a bit of money. And if you break a communication line, those are big money. So we, together with the regulator and the client, we decided not to excavate under the lines, and we estimated that the amount of soil that was left untreated that we didn't mix was probably 10% or less. And that was probably somewhat treated anyway by exposing it to the air and after putting the soil with persulfate back in the hole. So we were not too concerned about leaving a little bit behind. So the soil was excavated and mixed in 100 to 200 cubic yards batches, and like I said, within the excavation. And after the first mix, we collected soil samples, and during we also monitored, like I said, pH and limited residual persulfate. And actually at the very beginning, we saw that the first 3 or 4 batches, we saw that the pH wasn't too high. And that's when we said, okay, we gotta increase the lime dosage. And we basically doubled the dosage of lime. Luckily, lime is very cheap, and that did not have an financial impact on the project. Anyway, after the first mix, we analyzed the soil, and I'll show you results in a second. And we ended up remixing 1,500 cubic yards of petroleum contaminated soil to lower concentrations further. I mean, most of the soil, except those 3 or 4 initial batches, all the soil was meeting the industrial RUGs, but we had some concern that we would leave too much residual contamination behind, so some of the piles were remixed. We don't know the final results because we did not reanalyze those that were already meeting the action levels, but we know that we were for sure below industrial action levels, and possibly by remixing we lowered the concentrations even further. Like I said, during the mixing, we were monitoring pH, and we saw that it was dropping pretty fast after 1 or 2 days, and that was consistent with what we saw doing bench testing. Not so much in terms of pH dropping, because doing control environment in the lab, it stayed pretty constant. But we saw that the reaction was pretty fast, and pH dropping in the field was one of the indications that the reaction was probably pretty fast. And then we did some residual persulfate, PID. We saw consistent results with reduction of volatile compounds of about 65%, and we didn't see significant temperature increase and off-casting. This is a picture of how we started to mix the soil. So basically we excavated 100 cubic yards of soil, we added chemical inside the bucket, and then we were spraying water, mix, until basically we reached a cement-like consistency. After that, we left the soil in the mixing pit overnight, and the day after we would transfer the soil to the stockpile area, cover the soil with 6 mil polyethylene sheeting, and then let it react for 14 days. 14 days reaction. We had 32 stockpiles, and that was a decision we like I said, we had concerns. It was a risk. We didn't know if this was going to work, and if we were going to lower concentrations below the RACGs, below the action levels. So we preferred to keep this, we had a large space available. We preferred to keep the stockpile small so that if some were above RACGs and we had to dispose of soil, we could limit the amount of soil going to the landfill. And after 14 days, we conducted sampling. So basically for each pile we collected one incremental sample. I don't know if you're familiar with it, but incremental sampling is a new, relatively